Okay, so we're going to have a look at a video here on some of the aspects of the A-level electrochemistry specification from the CCE exam board. Still pretty relevant to those of you who are doing other exam boards, fairly significant amounts of stuff that's common between them all. Okay, so let's have a look. This is usually a topic that causes people some difficulties. So we'll have a look, we'll start at the start, we'll work our way through it. So we're going to have a look at pretty much at the order that the learning intentions are on the board at the minute. We're going to have a look at what electrode potentials are, have a look at how we would actually measure these electrode potentials, how we design half cells, depending on the half cell reaction that we're looking at, how we use these half cells and electrode potentials generated from them to decide if a reaction is or isn't feasible, how we then, and that's just qualitatively deciding if they are or are not feasible, then how we decide if a reaction is feasible based on working out its EMF, its electromotive force. We'll come to that as we get through the PowerPoint, and then having a look sort of at the end why some reactions which actually do have a positive EMF, which suggests that they are feasible, why those reactions actually do not happen. And the final thing is not on here, but we'll do some past paper questions and some general sort of in-class type questions as well. So let's kind of have a little look back at some GCSE stuff just to refresh us. And if we look at these two equations, if you remember back to GCSE, you did the reactivity series, and you learned at GCSE that zinc had a greater reactivity than copper. Yeah, you learned that other metals were more reactive than zinc. But really, what does that actually mean? Well, if you think about what happens to metals when they react, metals react by losing electrons. We can see in both the equations on the board at the minute that zinc reacts by losing 2 electrons, and of course copper also reacts by losing 2 electrons. Now, if we think about the fact that zinc is more reactive than copper, that means essentially that zinc is more enthusiastic about losing its electrons than copper. Or in other words, it takes less energy for zinc to lose its electrons than copper. So if I was to write this equilibrium, then I would suggest that that one lies much more to the right hand side, whereas the copper one would lie much further to the left hand side. So if we were to write an overall equation, we would say that zinc overall, whenever we combine these two half cells, when we react zinc metal with copper ions, zinc will more enthusiastically, let's use pretty inappropriate terms at the minute, but we'll get to the more technical chemical terms in a while. Okay, we'll go that way. And the copper 2+ ions will change to copper. Now, and that is exactly what did happen at GCSE. Okay, if you remember, we said that zinc was more reactive than copper, and zinc could displace copper from a solution of its ions. That was our displacement rule, if you can remember that far back. I know it seems like a long time now. Okay, so if I said to you, well, would copper be able to displace zinc? Well, hopefully you would go no, and we can sort of start to see the reasons why. It's all about the propensity of these things to either give up electrons, i.e. be oxidized, which is exactly what's happening to the zinc here, or the propensity to get reduced, which is what's happening to the copper 2+ ions down there. Now let's imagine we took these two equations and we didn't just take them together and shove them into the beaker with some copper 2+ ions in there and take a lump of zinc and let this reaction that we have up above happen. We could do that, okay? I mean, that's, of course we could. Okay, so we could just put the two things into solution or into a beaker and that could happen. Let's separate them out into two what we call half cells. Okay, so if we look at the diagram over on the right hand side of the screen, you can see we have two separate beakers. We have what we call half reactions, or we call them half cells. We'll call that one A and we call that one B. Now if we look at the chemistry that we did sort of back at GCSE there, we know now that zinc, okay, here is much more likely to lose its electrons, okay, and to turn into zinc ions that are in solution. Now the electrons are deposited on or left on the metal conductor zinc. Whereas over here we've established that the copper 2 plus, okay, is much more likely to take electrons, I should have that out of the other way, is much more likely to take electrons off the what would be the electrode. Okay, now for those of you who are on the ball, you can probably maybe start to think what's going to happen here. So the zinc side is willing to give up its electrons, and the copper side is going to take those electrons. Now that kind of results in one side pushing the electrons away and one side pulling the electrons towards it. If I then put, let's use a good old lamp, okay? If I put a bulb or a lamp into that circuit, there's going to be a movement of electrons, and that kinetic energy in those electrons will cause that lamp to light. We have now generated, through a little chemical reaction that we did at GCSE, we have now generated a flow of electric current which we can use to do work. Okay, that, and we'll get to this later, is called an electromotive force, an EMF. Okay, so just by simply separating our half cells, our two reactions that we have over here beside the red axis, okay, and connecting them with a conducting material, just a metal wire in this instance, we can now generate a current from these two half cells. And this is kind of the fundamentals of electrochemistry at A level. Okay, now it gets a bit more complex than that, but fundamentally this is what we're trying to do. Take half cells, combine them into an entire cell, and use that electrical energy, if it's there, to actually do work. Now, what we said here was that and let me just tidy this slide up a little bit before I talk any further. What we said here was that this half cell went that direction. This half cell went that direction. Now, that's a very descriptive term. Okay, it doesn't really help us that much. So what we're going to do, as we do in a lot of stuff at A2 in our final year of A level, we move from being qualitative, sort of descriptive, like I've just been, into quantitative, into giving these things actual values, actual numbers. And that's exactly what we're going to do now. We're going to generate what we call these E0 values, or electrode potentials. Okay? Now these electrode potentials are going to be numbers. And these numbers will tell us how far an equilibrium lies to the left-hand side or to the right-hand side in terms of gaining and losing electrons. Okay, and that's what they're called. They're called E0 values, or electrode potentials. Now these electrode potentials are numbers, okay, and they're numbers that we can interpret as telling us how far that equilibrium lies towards the side of oxidation or the side of reduction. And all of them are measured against what we call the standard hydrogen electrode. This is the standard hydrogen electrode on the board now. Okay, so SHE used to confuse the life out of me when I was an A-level student as to why my teacher was writing she on the board. It took a while for the penny to drop, but anyway, we got there. So the standard hydrogen electrode is shown in isolation on the left hand side, and then it's shown in combination with another half cell on the right hand side. So let's have a look at how the standard hydrogen electrode is first of all constructed. Okay, so this is what everything else is compared to. It's kind of like if you think about comparing masses to 1/12 of an atom of carbon-12. Everything is compared to that. That is the standard, and everything is relative to that. Okay, right, so we have hydrogen gas being bubbled in to an enclosed vessel, usually a glass tube, okay, into a solution of 1 mole per decimeter cubed of hydrogen ions. Okay, and that's important. These are the standard conditions under which a cell operates. Okay, the hydrogen gas is bubbled in at 1 bar or 100 kilopascals, we would say nowadays. Okay, and the temperature is 298 kelvins. Okay, I'll just make that a little bit bigger for you. 298 kelvins. Those are our standard conditions whenever we're dealing with the hydrogen half cell. And in fact, the standard conditions whenever we're dealing with any half cell at all. Okay, and the reason why we have to have standard conditions is so that whenever we measure one electrode potential, we can compare it directly against another, of course. Okay, you'll see down here we have an electrode, of course, for somewhere for the electrons either to be put onto or taken off, whether oxidation is happening or reduction. Okay, and that electrode in this instance is platinum. Okay, if you can't make an electrode out of the metal in the half equation, like we did in here, we were able to make it out of zinc and we were able to make it out of copper, both of which were in the half equations. We can't obviously do that with hydrogen because the half equation that's happening with hydrogen is, I'll just put it on the board, is as so. Okay, and there's nothing in there that is a conducting solid material. Okay, sorry, H plus ions are aqueous, excuse me. Okay, and the hydrogen is, of course, a gas. Okay, so that is the standard hydrogen half cell with which everything is compared to, and that is given a voltage of 0.00 voltage, and that does not mean it is unable to generate a voltage. What it means is that everything is compared to it. Okay, now let's look, we're comparing here to the magnesium half cell. This time we can make our electrode out of the magnesium. Let's write the magnesium half cell equation up here. Okay, so it's an equilibrium with magnesium. Now, you might have cottoned on to the fact that I've started writing all my half cells as reductions, and that is the standard way that we write half cells, as reductions, and then we can compare them directly. Okay, now we'll deal later with how we would deal with it were an examiner to write it as an oxidation. It's very simple, we would just flip it and we would flip this side as well. Okay, but anyway, let's have a look at the magnesium half cell. We can see again, if just about, the magnesium ions are in solution here, and they are in solution at again a concentration of 1 mole per decimeter cubed. The temperature in here will be, or in the whole thing, not just in here, 298 kelvins. There's no gas on this right hand side, so you don't need to worry about pressure of a gas. Now, this EMF, sorry, the voltage generated on the right hand side, okay, is calculated by putting a high resistance voltmeter into the circuit, and that high resistance voltmeter works by taking the electrode potential of the right hand side cell, the magnesium, okay, and minusing the left hand side. Now, if we put the hydrogen half cell on the left hand side, it has a voltage of 0.00 volts. Well, therefore, the reading that we get on the voltmeter is equal to the electrode potential of the right hand side, or the propensity of the right hand side to either accept or to donate electrons. The EMF is equal to the electrode potential of the right hand side in this instance. So let's say, for example, right, if I calculate out the magnesium, I can't quite remember what the magnesium magnesium reading is off the top of my head. I think it's about 2.3 V. Now, what does that actually tell me? Right, well, that tells me, okay, and this is the way to think about this, this is really important. This is negative, okay, it is more negative than the hydrogen half cell down here, which is 0.00 V. Okay, now, the reason why it's negative is because there is a greater buildup of electrons on the electrode. That's the way we can think about it. Okay, so if we did that compared to, let's say, that. So it's not that there's no electrons building up on the hydrogen, it's just relatively speaking there are many more on the magnesium half cell. Okay, that's why it's much more negative. That means that this equilibrium lies towards the side of oxidation because there are more electrons. That tells me, therefore, that this half cell must lie toward the side of reduction. So now I can start to build up a picture as to what would happen were I to combine these two half cells together. Okay, and I can use these E0 values for each individual half cell to start telling me in what direction the equilibriums would lie. Now let's say, for example, the next question was the examiner said to you, okay, based on these electrode potentials, would magnesium be able to reduce hydrogen ions? So we would go, all right, well, let's look at the magnesium half cell. It's more negative. Magnesium will go towards magnesium ions. And if we go down here, the electrode potential on the hydrogen half cell is more positive. That tells me that it is removing electrons and therefore lying towards the side of reduction. So in other words, hydrogen ions are turning into hydrogen gas. So my question was, can magnesium atoms reduce hydrogen ions? Well, yes, they can. The magnesium is going to get oxidized according to my arrow here, and the hydrogen ions are going to get reduced according to my arrow here. Next thing the examiner might say to you, right, okay, write an equation if these two half cells are combined in a whole cell. So what would happen? Magnesium undergoes oxidation and it goes to magnesium 2 plus. The net reaction in the hydrogen half cell is that the hydrogen ions go to hydrogen gas. They get oxidized. And that makes sense, because if you think about whenever you were younger and you added magnesium to acid, you got bubbling and you got the magnesium dissolving to, I don't know, magnesium chloride or magnesium nitrate, or depending on the acid that you added it to. So we can now, instead of going back to that sort of GCSE thing and going, oh yes, magnesium was above hydrogen in the reactivity series, we can now start to use numbers to predict whether reactions will or will not happen. And this is important for unfamiliar reactions. It's fine saying, going back here and saying, yes, zinc will indeed displace copper, because I know that from GCSE that zinc is more reactive, okay? But we're going to come across reactions at a level that are unfamiliar, and we won't be able to rely on a reactivity series from GCSE. Some of you may have noticed this part of the cell here, and it's here but not labelled. This is a thing called a salt bridge, and that's a really important part of a circuit. It basically completes the circuit and ensures that electrons can continue to move. Now, it is made of usually something like potassium ions and nitrate ions, potassium nitrate in other words. And the reason why these ions are used is because they're very, very stable. Okay? They do not get involved in the chemistry of the cell. And what they basically do is they keep the two half cells electrically balanced so the charge can continue to move. Let's take an example of this half cell that we have on the board. So we already know that zinc will have a greater propensity to get oxidized and go to zinc 2 plus, and we know that copper ions have a greater propensity to lie to the other side of the equilibrium, get reduced and go to that copper, pure copper. Now, we can't have copper ions or zinc ions in isolation on their own. They are, in this instance, copper sulfate, so there's positive and negative ions in the solution, and of course there's also zinc sulfate on the right hand side. Now, if we think about what's happening to the positive charge in the beaker, let's look at the left hand side first of all. The copper ions are being used up, so this beaker, but nothing's happening to the sulfate ions. So this beaker is going to become net negative. Over here the opposite happens. Zinc ions are being produced in the reaction, but there's nothing happening to the amount of sulfate ions. So this beaker over here is going to become net positive. Now, if you remember, it was the zinc that was giving up electrons and the copper that was attracting them, in other words, undergoing reduction. Now, if this half cell over here becomes net negative, remember it's electrons that are moving around the circuit, sort of, okay? It's electrons that are moving around the circuit. That means that a negative half cell over here and electrons coming towards it, we're going to experience repulsion. So they're going to slow down, maybe even send back those electrons. Over here, this is becoming net positive. So the electrons that were meant to be going across the cell to light my lamp or power my phone or whatever, okay, are now going to be attracted back by the positive charge. That means whatever I design my cell to do, it isn't going to do it. So how do we get over that? Well, this one becomes net positive. So from the salt bridge, my nitrate ions will gradually make their way in. That neutralizes the overall electrical charge in that half cell, therefore preventing what I've just spoken about. The opposite happens over here. This one is becoming net negative, and the positive potassium ions will make their way into the half cell, therefore neutralizing the net negative charge. Okay, and it basically completes the circuit by keeping the balance of charge neutral. Right, what if a half cell reaction doesn't have a conductor in it then? How do we design half cells? If we look at this half cell, and I'll get rid of all that stuff there and tidy it up, we can see it's pretty easy to design our half cell here, because the zinc metal is a conductor, so I can use that as my electrode. The same is true over here. Okay, my copper is going to copper 2 plus, and I have copper as an electrode. Very simple, but that doesn't always happen in the half cells that we're going to investigate. So let's have a look at this half cell here. Hopefully straight away you can see the problem. We're going to investigate the electric potential of the redox reaction between iron 3 and iron 2. Iron 3 is aqueous, dissolved in water. Iron 2 is aqueous. So how do we get over that? How do we investigate the electric potential of this half cell without having an electrode that we can make out of one of the substances in the half cell? Well, very simply, we use, in this instance, an inert, unreactive conductor. So platinum is generally the one of choice. And that means that we have an interface that we can allow electrons to build up on, or electrons can be removed from, depending on whether the net cell is undergoing reduction or oxidation. And you'll meet lots like that. Let's have a look at another one. We've kind of looked at this one already, where we have a gas. Okay, so we have a solid electrode on the right hand side here, or silver. Okay, and on the other side we have a gas. So we have another sort of issue that we have to deal with. But again, we just have an enclosed capsule electrode, okay, where the gas cannot escape. Okay, and we have again a platinum electrode dipped in a solution, in this instance a solution of course 1 molar hydrogen ions. So that's how we would deal with gases, that's how we would deal with solutions. If we have, let's say, more than one ion in a half cell, so this one here, if you look at it, we've got chromium, hydrogen ions, chromium 3 plus, and water involved. Well, very simple, it's not really any different. We just, again, we have to have a platinum electrode. There's nothing suitable in that overall half cell that can act as an electrode, and we just mix our ions that are involved in a 1 molar concentration. Okay. Right. Now, we've seen a lot of cells here. We've seen 2 half cells joined together. Of course, if you look at this one, 2 half cells joined together, those are called a cell. And I'm sure your physics teachers always went on at you about not talking about a battery, talk about a cell, or don't talk about a cell, you talk about batteries. And so if I was to ask someone in class to draw me a cell or illustrate a cell like the one on the board, 2 half cells and a cell like the one on the board, that is a really laborious, sort of protracted way to go about it. So chemists have come up with a much more efficient way of representing cells. So if we look at this cell that we have on the left hand side, if we had to write that out every time, that would be a significant hassle. So we have come up with this shorthand method here called the conventional cell representations. Okay, now there's a set of rules to follow. We'll look at the rules, okay, for first of all writing half cells, and then we'll look at the rules for combining those half cells into cells to see how we can take this rather laborious looking cell on the left hand side and turn it into a shorthand cell on the right hand side. So let's look first of all at how we write half cells. So the electrode is placed on one side of a vertical line. Okay, so if we go down to these first couple here, the electrode in the first one can be zinc, so we put it on one side of a vertical line. Down here we have two aqueous substances, so our electrode this time has to be platinum. But again, put a vertical line beside the electrode. Second rule, the species in solution, whether solid, liquid, aqueous or gas, are placed together on the other side. Well, that's dead easy for this one. We only have one other thing, zinc 2+. Down here we have iron 2 and iron 3. Okay. And down here we have a platinum electrode on the one side of a vertical line, and then here we have chlorine and chloride ions. So there you go on the other side. Right. If there's more than one species, okay, and they're on different sides of the half equation, they're separated by a comma. So you'll see the comma here. Okay, the iron 2 is iron 3 is on the left, the iron 2 is on the right. So we have a comma. Okay. However, if they are in different phases, which is exactly what we have in the next half cell down, because chlorine is a gas, chloride ions are aqueous. If they're in different phases, they are separated by a solid vertical line. Okay, you can see my wobbly solid black vertical line there. So don't need it here. They're not in different phases. Aqueous, aqueous. Okay, do need it down below. So those are your half cells. You can write half cells now. Let's look about combining them into full cells. Okay, the more positive electrode, okay, then is always placed on the left hand side. So the more, we looked at electrode potentials earlier, and the fact that some were positive, negative, less positive than others, more negative than others. So the more positive one, if we can remember, let's just go back to our, because we haven't done very much of this, so people are probably still a wee bit vague on this. We said that our hydrogen half cell had electrode potential as such, and I said our magnesium half cell, which I did say earlier, I can't remember the electrode potential value off the top of my head. I think it's about -2.34 V, but anyway, I can't stand corrected. Okay, so the more positive one, going back to this, is placed on the right hand side. Well, this is the more positive one. Okay, and that is the one that reduction is always taking place at. Okay, so it's easy to remember, reduction on the right. Now you might be going to me, well, on the right hand side of what, sir? What are you talking about, the right hand side? Right, the two cells are placed on either side of two vertical broken lines, which represent that salt bridge. So when I talk about the right hand side, I'm talking about the right hand side of my salt bridge. Okay? Right. The electrodes are placed on the far left hand side and the far right hand side. So there we go, from our half cell writing earlier, my two electrodes. On the left hand side, the lower, so this is the oxidation side. Okay, on the left hand side, the lower oxidation state species is written first. Now, let me just tidy this up a little bit for us. Okay, so in this one here, it doesn't matter. There is no lower oxidation state species apart from the electrode. Down here, we can see that hydrogen, the oxidation is going from hydrogen to hydrogen ions. So that is oxidation. Okay, my electrode is platinum, so now I have the lower oxidation state species 0 first, and then the higher oxidation state species second. Remembering they're in different phases, gas and aqueous, so therefore we have a solid line. If we go down to the next one down, we have iron 2 getting oxidized to iron 3. Okay, platinum is my electrode, they're both aqueous, so my iron 2 is written first, lower oxidation state species first, but they're separated by a comma this time because they are both, as you can see there, they are both aqueous. Okay, on the right hand side then, the higher oxidation state species is written first. So if I go back up to the top equation up here, we can see that the right hand side is reduction. This time the hydrogen ions are getting reduced. And here then my higher oxidation state species is written before my lower. They are in different phases, gas and aqueous, so we have our solid line. Okay, so that is how you then take your half cells from the previous one and you turn them into full cells. Okay, so I want you to draw cell representations for the following. Okay, so probably pause the video now and do those. I'll pop the answers up, and when you finish that then I want you to use the information from the previous rules. You maybe want to take a photograph of those. Okay, I'll go back to them in a wee second, and you're going to work out the overall reaction that's happening based on the information there. So there's your half cells, take a photograph of those if you need to. And there's your cell reactions and how you do those. Take a photograph of those if you need to. Pause the video. Alright, so pause the video now and start those questions. I'll put the answers up. So we'll do A here. Put our salt bridge there. Reduction goes on the right hand side, so there's my reduction. Okay. I can use copper as my electrode, so I'm going to put there Cu and there's Cu2 plus, dead simple. Here I can use iron as my electrode, so line to there, Fe, and then I have Fe2 plus. Dead easy. Let's do B. Okay, so B, what's getting reduced is iron 3 is going to iron 2, so on the right hand side I am going to have platinum because I can't use either of those. Okay, I write my higher oxidation state species first and my lower oxidation state species second. They're both in the same phase, so they're separated by a comma. On the other side of iodide, iodine, I can't make an electrode out of either of those. Okay, this time I have oxidation happening, so I have lower oxidation state species first. They're both in the same phase, followed by higher oxidation state species. C then, I have again put my salt bridge in. I've got zinc here, okay. Zinc is getting oxidized, so it's going to be on the left hand side. I can use zinc as my electrode, it's a conducting metal. Okay, it goes to Zn2 plus, dead simple. Okay, on the other side I have hydrogen ions and hydrogen gas, so I need platinum as my electrode. Okay, I write higher oxidation state species first here, which is hydrogen ions. They are aqueous and my hydrogen is a gas, so I'm going to separate those by a line. Okay, hopefully you got those right. Let's have a look here and we have to work out the equation. So remember, on the left hand side we have oxidation. So oxidation, that must be going to that. So zinc is going to zinc 2 plus. And here I have Fe3 plus, so that's reacting with Fe3 plus, is going to Fe2 plus. Now what we do need to be careful is when the zinc does that, it loses 2 electrons, but when the iron goes here to here, it's only gaining 1 electron, so I need to balance out my charges. Okay, let's go down to the next one. Right, B then, my oxidation is iron 2 is going to iron 3, so put my arrow in. Let's put iron is going to iron 2, not iron 2 to iron 3. Rubbish. Remember just ourselves there that involves the loss of 2 electrons, and then here iron 3, so let's put that in there, is going to iron 2 as well. So I could put plus Fe2 plus there, but I'm just going to do that. Okay, and that is gaining only 1 electron, remember, so I'm going to have to multiply my iron 3s up by 2 and that up by 2. Okay, so that means I have 2 iron 3s, and I'm going to need an extra iron 2, so that you should see your charges and everything. I'm sorry, I missed a positive sign there. You see your charges and everything balanced out there. Finally, let's look at C. Okay, so we should be getting the hang of these now. Oxidation, so let's put our arrow in. Silver is going to Ag plus, remember that is loss of 1 electron, and chlorine is going to chloride. Here's where you need to be a little bit careful and remember that there will be 2 Cl minuses there, yes, and that will be gaining 2 electrons, yeah, so it has to have 2 silvers because we need 2 electrons from it, and that again, should the charges are balanced, the atoms are balanced, everything is balanced. Okay? Okay, so this video is at the minute, it's 35 minutes. I've still got a lot to do in this, so I'm going to call that quits for that particular video, and then we'll have a look in the next video about how we actually work out these, use electropotentials, so actual numbers, to work out whether a reaction will or won't happen, and then we're calculating out EMFs. Okay, so hopefully that helped to get you going. We'll come back in video 2 and get stuck into the calculations and the numbers a little bit more than we have so far.